All right, welcome back. Today we're going to continue with searching and sorting. We'll probably get it through it this week, but then when we come out back after break, we'll go ahead and review as needed and then move on to the last topics for this course. So when we left it off last time, we had covered two searching algorithms, linear search and binary search, and then a couple of sorting algorithms, selection sort, which we actually implemented, and then quick sort, which we gave the idea of, but then ultimately we said that all four of these things, you're not actually going to implement them in practice. Instead, what you're going to do is you're going to use the built-in searching and sorting algorithms that are provided by the language that you're using at the time, and in particular in C, you'll use what's built into the standard library. Now, we quickly gave an idea of how this works. Basically, you have a sorting algorithm, a generic sorting algorithm here that knows how to sort. It knows that if these two things are out of order, it needs to exchange them, and it does it for everything, right? For selection sort or for quick sort, it says, here's a pivot element. The things that are less go over here. The things that are greater go over here, and then I'll recurse on it, use recursion on it. Unfortunately, to make this generic, it doesn't know how to compare these two elements, A and B. So what we need is this other thing called a comparator that we give as input to this function that whenever it needs to determine, does it go on that side of the pivot element or on that side of the pivot element, or are they out of order and therefore I need to swap them? It doesn't ask that question. Instead, it says, I've got A and B. Are they in order, out of order, or are they equal? It passes that off to this comparator. The comparator looks at them and says, okay, these are integers that I am comparing, and therefore I will return something negative if A comes before B. I will return 0 if they're equal, and then I'll return something positive if they're out of order. And by returning one of those three things back to the sorting algorithm knows that they should be swapped or they should be left alone, for example. Ultimately, that means that you only need one sorting algorithm, one searching algorithm for any type, integers, doubles, characters, arrays of characters, strings, right? Or built-in type, or user-defined types like films or students or what you're doing this week in lab teams, right? So to understand that a little bit better, what we've got to do is we've got to lay some groundwork here first. How do I pass this comparator thing that is basically a function, how do I pass that off to another function so that it can use it, right? So how do we pass a function to another function? Right? Doing so is generally referred to as a callback. Right? So the function that we're actually passing into this other function, that's what's called a callback. Basically, it allows the function to call the other function back, right? I don't know where the term callback comes from, but it's a callback. It's a recollection from before. So if you're given this thing, you can always call back on it, right? You can call back to it, right? It happens all the time, right? For graphical user interfaces, graphical user interfaces. We'll see this later on after the break where we design some graphical user interfaces. You need a callback. For example, if you create a button, right, you need to specify what happens when somebody clicks that button. So when you create this button, you also give it a callback so that you register this callback with that button so that when this button gets clicked, you don't write any of that code. When this button gets clicked, it says that call that function over there or call that function over there instead, right? So that you don't have to put all of that code in the button code. Instead, it's just generic button code that says, I should be calling a function when I'm clicked. Which function do I call? Whichever one you gave me as a callback. I don't need to know anything about that function other than I need to invoke that function, and that's it. Just like the sorting algorithm doesn't need to know anything about A and B in order to invoke this comparator. It simply takes A and B and gives them off to this comparator. That's what's known as a callback. It's calling it back, basically. An example here is quicksort, Q sort. We'll go ahead and show you how to use this later on here, but it needs a comparator, a function, in order to order items, right? It needs to know, does A go before B or does B go before A, right? So how do we do this, right? So consider, what is stored in memory? Well, data is stored in memory. What else is stored in memory? Files are stored in memory. In fact, what's not stored in memory? Where does a computer store things if not in memory, right? So in other words, everything gets stored in memory, and it also makes sense that functions are stored in memory, right? And even before that, your program is a file, basically. Your program is stored in memory. Right? And since your program consists of a bunch of functions, that means that those functions are stored somewhere in memory. As a result, you can create a pointer that points not to data, not to a program, not to we've done this before. We've created pointers that point to data. We've created pointers that point to files. And now what we're going to do is create pointers that point to functions. So you can create a pointer that points to a function. What does that look like? Here's the syntax. So suppose we want to create a pointer to a function that takes a double, an integer, and a character, and returns an integer, an int. There we go. We'd create a pointer that looks like the following. And for this, I'm going to go ahead and go over here into code mode, or into the CS50 IDE here, okay? And demonstrate how we might do this. So it returns an integer, so we're going to go ahead and put that in there, right? And then we need to give this variable a name. If I were to create a pointer to an integer variable, for example, if I said int star a, right, or ptr to int, I'll put it like that. This creates an integer pointer. What is the variable's name? It's ptr to int. So I'm going to do the same thing here, but because of order of precedence, I'm going to do it inside parentheses here. So this is going to be a pointer to func, where func is just a function. Right? Now I need to specify that it takes a double, an integer, and a character. So a double, an int, and a char. Right? There. That creates a pointer. This creates a function pointer that can point to any function that, one, takes a double, int, char as inputs and returns an integer. So where is the return type specified right here? Right here, int. The name of the variable is ptr to func. And you know that it's a pointer because we've got this star right here. This is why I needed parentheses. If I didn't use parentheses and I put it right here, what would that tell me? That that's an integer pointer. It returns an integer pointer. Nope, it returns an integer. Okay? And it takes a double, an int, and a character as inputs. Right? So let's go ahead and create a function that does that. Int, I'll call it foo, that takes a double, x, integer, y, and a character, c, as inputs. It doesn't really matter what this does. We'll just go ahead and return x times y. Right? So I've got this function foo here that matches the signature. It returns an integer, it takes a double, an integer, and a character as its inputs. Now, at this point in the program, what does ptr to func point to right now? Well, let me turn the question around. What does ptr to int point to right now? Garbage, dead beef, null? What? If you want to make it point to null, what should you do? Explicitly make it equal to null. Now, if you want to make this explicitly equal to null, you can do that as well. Right? And now the answer is it points to null. But what was the original answer? Dead beef. Random memory location that doesn't exist. Random memory location that doesn't belong to you right now. Right? All right? So it is undefined. And therefore, using it, it would be undefined behavior. So let's make it point to null. How do I do that? How would I do it with ptr to int if I didn't want to do it on the same line? Ptr to int is equal to null. Same thing below. Ptr to func, pointer to func, is equal to null. Right? Now, Can I call that function? Well, there is no such thing as the null function. So I would get a pointer dereference, and Bret Hart should be hitting you over the head that you dereferenced a null pointer. Don't do that. Right? Let's make it point to foo. How do I do that? ptr2func is equal to, now how do I get the memory address of a function? Well, I can get the memory address of an integer. If I just have a regular old integer here, x, how do I get the memory address of x? Ampersand x. Same thing here. Ampersand, and then what am I trying to get the memory address of? Foo. Right? You can do it that way. Or, even shorter, you don't even need to use the ampersand. ptr2func is equal to foo. Right? Because the function name itself, a function's name itself is its reference. Just like we've seen before with an array. When I create an array, what is its memory address? If I create an array called ARR, what's its memory address? ARR. Right? So foo is the memory address of foo. Right? And you can just use this as shorthand. It's not wrong to do it that first way with the ampersand, but why write more when fewer do well, right? Whatever the quote is from Office, right? Why use many words when few words do, right? All right, so keep it simple. So now once we've got this, how do we use it, right? You can invoke a function like usual. For example, if I wanted to call foo, I would call it foo, and then I'll pass it a double, 3.5, 10 for the integer, and capital H for the character. And then if it returns a value like this one does, then you would put it into a variable. Int result is equal to foo. Right? You can invoke a function like usual, but how do you invoke it through its pointer? Or you can invoke it via its pointer. So how would I do that? Well, once I've got a pointer to it, basically that's an alias to it. So 3.5, 10, and H. There we go. That's exactly the same. So why do I do this? Why do I want a pointer when I've got a perfectly good function name called foo? Right? The reason that you want to do this is so that you can pass it to another function that then calls that function. For example, what if I created a function called runMath? Right? And I will go ahead and call and say that this returns a double, and say that it takes an input, a double input, and then it takes another function as input. It doesn't take another function result as input, it takes another function as input. What would that look like? Double, star, and I'll just call it F, right? And it takes a double. So I'm calling this runMath Y. What math functions take a double and return a double? Sine, cosine, square root, tangent, right? If I wanted to pass one of those off to this function so that it could call it, it would look something like this. Right? I could pass in sine, I could pass in cosine, I could pass in square root, whatever, and I'll simply just return f sub input. Now, what is f? Well, it depends on how you call runMath. It could be sine, it could be cosine, it could be square root. Let's take a look and see how it works. All right, so double y is equal to, normally if I called, say, square root of 2.0, right, printf, y is equal to %f and the line. There we go, y. Right, this is me using the math library as intended. So GCC, function pointers, right, and then run this, a.out. There. That's the square root of 2, right? What if I were to create a function pointer that pointed to the square root instead? What would that look like? It would look very much like this up here, but it would look different in that it returns a double and, I don't know, math PTR, right? And it takes a double as input. Right? And there, that's all I need. Now, as an aside question here, math PTR is equal to, say, foo. Could I do something like that? Remember, PTR to func was defined as something that returns an integer and takes 3 inputs, a double, an int, and a char. Foo takes a double, an int, and a char. But does math pointer? It only takes 1 double and it returns a double. Is this thing on line 42 the same thing as this thing on line 19? Certainly not. Just like a pointer to an integer should not be made to point to a double, or vice versa. One of them will assume that it is 4 bytes, and the other one will assume that it's 8 bytes, and you will get unexpected behavior, undefined behavior, if you go mixing those two things together. It's perfectly fine to do this. In fact, you might not even get a warning. Let's find out. Yep, okay, good. It gives a warning because this double is not the same thing as int, double, int, char, right? But it's just a warning. That's perfectly fine. Go ahead and do whatever you want, I guess, right? But that's not how you should do it, right? So, careful. Make sure the types match. Right? So I'm going to go ahead and comment this out so I don't have to deal with that warning anymore. How do I make math PTR point to, say, square root? There, something like that. Now, when I can invoke this directly by saying y is equal to math PTR of, say, 2.0, and printing that out again, and I will get the exact same result as before, but instead of calling the square root function directly, oops, now I have to use that -lm here. Now instead of using the square root function directly like I did on line 39, now I'm doing it circuitously by using this pointer here. And I should get the same result though, right? And I do, because it's invoking that other function over there. Well, I don't have to make it point to square root. I could make it point to sine instead. So what's the sine of 2.0? Anybody? I don't know, we'll find out here. 0.9? Right. And that's radians, remember, two radians. I could make it point to tangent, right? GCC, run it again. What's the tangent of 2 radians? Okay, negative 2.1, apparently, right? So this allows me to call a function circuitously. It also allows me to pass in a function to this other function up here, run math, right? So I can say y is equal to run that math on 2.0 with square root, and then print it out. Or I can run that math on sine. Or I can run that math on tangent. And now we'll see that we get all those results that we just witnessed. I can pass this function off to another function so that that function can call that function. Right? Imagine how this might be useful. Again, I don't want to bring calculus into this when we don't have to. But what if I had a function that did Riemann sums, that did integrals? Now, if I did the integral of a particular function, say square root, then I would have to write that function, the Riemann interval sums for square root. Right? Now what if I wanted to do it for sine? I'd have to write another function, Riemann interval sums for sine. Right? But what if I created one generic Riemann sum function that took another function as its input? Then it could do the Riemann sums itself, right? And I'd only need one implementation of it. Likewise, what if I created one sorting algorithm that didn't know how to order A and B? It didn't even know what these things are. It doesn't know if they're integers, doubles, or whatever else, but it could pass them off to another comparator so that that comparator could tell it that they're in order, out of order, or they are equal. Right? That is the power of passing a function to another function as an argument. Right? You can use it as a callback so that you can write one function that has multiple behaviors, multiple functionalities. Right? Okay, questions so far on this? All right, I'll make sure that this is in the notes here so that you have it. There we go. But otherwise it's also in the book, right? In my book. I don't know how well Zybooks covers this, but in any case. So, sorting using QSort. So the first thing that we're going to need are comparators. Creating comparators in C. Right? Let me find my location here. So what is a comparator? It's a function. Oops. A comparator. And I don't know if that's a comparator. I don't know what the actual word is in English, but I don't even know if that is a valid English word, but whatever. It's something that compares things, right? Has the following signature. Right? And for this, I'm going to go ahead and cut and paste it so that I don't have to type it out. There we go. And zoom in a little bit. There we go. Right. Good. Yeah, thank you for correcting the quote online. It is, why use many words when few words do trick? Thank you. This is from The Office. Kevin. Right. So here's a comparator function, right? And it follows the same basic contract right here. What does it return? It returns an integer. That integer will be something negative, positive, or something positive, or 0, depending on the relative ordering of its inputs, A and B. So let's make a few observations about this, first of all. Right? Again, it returns an integer with the following contract or expectation. Contract. There we go. Again, it returns something negative if A comes before B. It returns something positive if A comes after B or B comes before A. And it returns 0 if they're conceptually equal to each other. Right? Now note there that I have emphasized the word something. It could return -1. It could return -42. Don't read anything into the magnitude of that number unless you want to design it that way. In general, you can make no expectations on the magnitude of those numbers, though. It returns something. Right? Another observation. What values are A and B? First of all, they are const, right? What does that tell you? You can't change it. In fact, the comparator won't be making any changes. The comparator cannot make any changes to the input values, right? That's good. The sorting algorithm will be, right? The sorting algorithm will be swapping things back and forth. It'll be making changes to the array, but it will not be making changes to the individual elements, A and B. It's just going to be moving them around, right? Second, they are both are void star variables. What is a void star? Where have we seen that before? Yeah.
It's any pointer.
Any pointer, right? It is a generic void pointer, right? It can point to anything and any type. You have to keep it like this because sometimes you will be sorting an array of integers and other times you'll be sorting an array of doubles, right? You can't hard code that it's always going to be an integer. That's not a comparator. You can't hard code that it'll always be a double. That's not a comparator either, right? You have to keep these generic, okay? Where else have we seen void pointers before again? What returns a void pointer that we then have to typecast to force it to become a specific type of pointer? Malloc. Right? This is why we don't have a malloc for integers, a malloc for doubles, a malloc for films, right? We tell it how many bytes we want, and then it returns a generic chunk of memory of that size. However you use it, that's up to you. Right? This is so that we can write one malloc function and not have to worry about that problem ever again. Likewise, we're going to write and actually just use one sorting algorithm and never have to worry about that problem again. Right? A comparator follows a basic pattern. Right? Comparator, there we go. First, it typecasts the given variables into a specific, that is non-generic type. Why? Because it does need to know something about these. Now, the sorting algorithm doesn't need to know anything about A and B, but certainly the comparator does. The comparator needs to know that these are integers, the comparator needs to know that these are doubles, or the comparator needs to know that these are films in order to do its comparison. If it doesn't know anything about them, it also doesn't know how they order. Does A come before B or does B come before A, right? So it has to force them to become specific variables, just like you force that generic void pointer returned from malloc to become an integer pointer or a double pointer or a film pointer, right? Once you've done that, you make a comparison based on the state of the variables, right? Avoid the difference trick. Avoid all tricks, right? Make liberal use of other code, right? Those are three outlines, guidelines, I should say, that I'm going to give you, and now we're going to illustrate it when we come over here and do some actual examples, all right? So let's come back over here, and let me go ahead and get rid of function pointers over here. And let me go back to the demo that we were already developing. I'm going to go ahead and get rid of all the searching and sorting algorithms that we've already developed, because we don't need them anymore. Now that we've got function pointers and we've got comparators, we can use the built-in functionality just in the standard library. I will still bring in films, because eventually I'm going to show you how to compare this film to that film. Arrival should come before Dune because it was released first, or lexicographic order or something like that. By the way, I've been pronouncing his name wrong this entire time. It's Denis, not Dennis. Right? So I only ever read his name. So sorry, Denis. I was mispronouncing your name. Right. I'm also going to get rid of all the code that we've used up to this point for searching and sorting, because now we're no longer going to rely on our custom code. We're not going to roll our own. We are going to use what's in the standard library. So the first thing I need to do is, I've got this integer array. I want to sort this integer array. So I need a comparator for integers. So let me come back up here, and let's go ahead and create a comparator for integers. Comparator. Actually, let me go ahead and document this fully. Right? So this comparator orders integers in... There's more than one way to order an integer, right? I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or what's the other way that I could order an integer? Descending order. So which one do you want? We want descending? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1? The natural ordering, sometimes people, languages call it the natural ordering too, is ascending. We will definitely want to do descending, but let's do that in the sequel here. Right? So this comparator orders integers in ascending order. All right? So what should the prototype look like? Or what should the signature of this function look like? Int, CMP, int A, int B. Is that a comparator? Nope. Does it look anything like this? No. Only that signature is a comparator. Okay, fine. You want pointers instead, right? You want unmodifiable pointers. Const int star A and const int star B. Is that a comparator? No. It is not generic. Right? Only something with this signature is a comparator. Anything else is something completely different. It's not a comparator. Right? So strcmp, is that a comparator? Let's find out. There's the signature of strcmp. Is it a comparator? Not technically. Const char star, not const void star. So technically, strcmp, even though it follows the same basic pattern of returning something negative, positive, or 0, depending on the relative ordering of those two strings, it is not a comparator technically. And you cannot use it with the built-in searching and sorting algorithms. You can use it as a subroutine, and I'll show you how eventually. Right? This is a comparator for integers. Step 1. What we need to do, I can't do anything with those. Those are just raw memory addresses. It doesn't matter if that thing is stored in that memory address and that thing is stored in that memory address. Great, that memory address is greater than that memory address. That doesn't tell me anything about the elements themselves. 5 and 10, what order do they go in? 5 comes before 10, right? What I need to do is I need to cast them into a proper expected type. For this particular function, we are expecting integers. So const int star x is equal to const int star of a. What I've done is I've created a local variable here, x, that is still const, so I'm keeping my promise. I can't modify a, so therefore I can't modify x. When I make x point to a, and I'm now forcing that void thing to become an integer. It's still a pointer. You can dereference this if you really want to up front, but I'll do that later. And I'm going to do the same thing with b. Now I have some information about the input types, that they're integers, and I can make a comparison. So how do I make my comparison? If x is less than y, then return something. Now, is that how you should be comparing integer pointers? Nope. That's, again, the memory address. Does that memory address come before that memory address? That doesn't tell you that 5 comes before 10. Right? So what do I need to do to those things? What do I need to do to this pointer in order to make it into a regular old variable so that I can make a comparison? Dereference. Dereference. If you really wanted to, you could, of course, make int, and then we've run out a, b, x, y, jk maybe. I could say j and k, and then I could dereference those and then make comparisons between j and k. This is just as good though, right? So what should I return here? The value stored in x is less than, strictly less than the value stored in y. Are they in order or not? X comes before y, so they're in order. What should I return? Negative 42. Oh, should I return 0? This is strictly less than this. 5 is strictly less than 10. So I should return, they're not equal. When do I return 0? When they are equal. Right? So I should return negative 42. Right? Why do some weird number like that? Just do negative 1. Right? Else if, what if x is greater than y? Are they in order or are they out of order? Again, up here this was in order. So return something negative. Here, they are out of order. So what should I return now? 1. Okay. Again, you could have returned something positive, 42 positive. Right? Why be weird about it, though? Just return 1. Right? Else, now what's the only other option here? Is that they are equal. And here, I return what? 0. Right? So did we talk about the difference trick? No? Okay. We did? Okay, we did. Avoid the difference trick. Here's the difference trick. What if I had just done return x minus, or y minus x? Is that right? Yeah. Yeah, go ahead.
You fall victim to overflow or
Exactly. You fall victim to overflow or underflow. Underflow, right? 10 minus 5 here, that's going to be positive, right? So they are out of order. But if I went with 5 minus 10, then that's equal to negative 5. And so they're out of order, and so you'd return something negative, negative 5. If they were equal, 5 minus 5, then you'd return 0. But the problem here is what happens when you've got 2.147 billion, 147, 123, 123, and minus negative 2.147 billion, 123, 123. Yep, there we go. Right? So 2 billion minus negative 2 billion is going to be positive 4 billion and change. Can that be stored in an integer? Nope. Don't do that. Also, what if these were doubles instead? What would this look like instead? Let me go ahead and cut and paste this. And let's create a comparator that orders doubles in ascending order. Well, first of all, can I name them both CMP? No. So I should probably go back and rename this. It's a comparator for what? For integers in ascending order. Okay. This is a comparator for doubles in ascending order. Now, how does it differ from that one up there? Instead of integers, I'm expecting doubles, doubles, and doubles. Now think about the difference trick here. What if I did a difference trick here? Say that it's return y minus x. Right? Let's suppose that it's, say, 3.5 minus, actually, let's go with 3.75 minus 3.25. What's the difference there? Positive, right? It's 0.50. But what gets returned? Yeah, an integer. Why? Because that's what the signature is. So 0.5 becomes what? 0. And is 3.75 equal to 3.25? Nope. So don't do that. Again, tricks are for kids. Don't do that. All right. Before we start using this, though, let's think about other ways that we could, or other kinds of comparators that we could come up with. What if now, here's the sequel, what if we want a comparator that orders integers in descending order? Well, I can't call it ascending anymore. What should I call it? Desk. All right, descending. I would have the same exact pattern here, though. I would typecast them to integer pointers. And the only difference here would be what? Greater than. Change the less than to greater than, or greater than to less than to greater than. But otherwise, it's the exact same pattern. Lots of repeated code. Lots of repeated code. Is there a way that we could get away with less code? Again, the quote, why use many words when few words do trick? Return -1 times the other one, A and B. I like that, right? Now instead of 15 lines of code or whatever it is, it's 1 line of code. There's a game called Code Golf. All right, so in golf, the fewer number of strokes wins, right? You want to, if a hole-in-one is the best you can do. If it takes you 15 strokes to get the ball in the hole, though, that's kind of bad. So Code Golf works in the exact same way. How can you get the exact same behavior, but with fewer lines of code? And if you only have 1 line of code, how can you get it to fewer characters? So Code Golf, how could we get this to even fewer characters? You don't have to multiply anything. You can always just go minus. Right? Can you do better? There's also another game called Name That Tune, where people would say, I'd be able to name that tune with 3 notes, or 10 notes. I can name that tune in 5 notes. I can name that tune in 3 notes. All right, fine. I challenge you. Go ahead and name that tune. Can you name this function with even fewer characters? B, A. Right. I think that that's as good as you can do. What did I do there? I'm just returning the value, but I've switched A and B. And so therefore, up here, X and Y will get the opposite values, meaning that the strictly less than and the strictly greater than have swapped orderings just by me swapping the parameter variables. Right? Now that we've got all 3 of these things, let's go ahead and try and use them. First of all, we need to understand QSort. Right? So QSort. There we go. Let's see. C provides a standard quicksort implementation. It's actually not necessarily quicksort, but because it was named that originally it was a quicksort implementation. I think if you look under the hood, most implementations are not quicksort anymore, or they're certainly not recursive versions of quicksort. They might actually be like some sort of merge sort, or there are dozens of other sorting algorithms out there, but they're fast. Right? They're fast. They're optimized. They are bug-free. 99.999% with a surety there, etc. It takes 4 arguments. All right? What are those 4 arguments? The first one is base. Right? Base. There we go. This is the array you want sorted. Let's make some observations about that. Is it an array of integers? Not necessarily. Is it an array of doubles? Not necessarily. What is it? It's a generic void pointer. It's an array of things. Again, the sorting algorithm doesn't know anything about those things other than they're things. Okay? So it is a generic array of things, stuff. All right? It does not have the const keyword. What does that imply? It's going to be making changes. What changes is it's going to be making? It's going to be resorting the array. It will change the array you give it. Right. Okay, well, that's what I want. If you don't want that, make a copy, sort the copy. All right. Nel is short for number of elements, right? That's the number, the size of the array, the number of elements in the array, right? We always have to do that anyway. Any function that you've ever written that deals with arrays, you've passed in the array and you've also passed in the size of the array. So that's not new. What about size? Well, terrible name because we've already have the concept of size with nel here, right? Size is the number of bytes each element takes. Why would quicksort need to know that? These two things are out of order. It needs to swap them. What does it need to know? The number of bytes. If this is 4 bytes, 8 bytes, 50 bytes, it needs to know how many bytes to take and put into a temporary variable so that it can take the same number of bytes, 4, 8, 50, whatever, copy it over to this location, take these 50 bytes and put it back over here. Right? It doesn't know anything about the elements that are stored in there, so it needs to be told how many bytes it should be swapping. Right? Finally, and by the way, how do we do that? Right? Use, what macro do we use for the number of bytes that an element takes? Size of. Right? There we go. Finally, what is that last thing? Compare is a, well, what is this thing? What is the syntax right here? It's a function pointer that points to a, what kind of a function? A comparator function. A function that takes two const void star inputs and returns an integer. And you know that it's a function pointer because of this syntax right here that we just introduced. You won't have cause to write your own functions that look like this, but you should understand how to use functions that look like this. Okay? So it's a function pointer that points to a comparator. Excellent. So let's come back over here and use it. Qsort. It doesn't return anything, by the way, because it just does its work and then it returns. It's not giving you a new array. It's not giving you a 0-1 error code, success, not success, or whatever. It assumes that you know how to use it, and that if you don't know how to use it, then the entire program will crash anyway. Right? So quicksort, it takes 4 arguments. The first argument was what again? The array that you want sorted. What's the array I want sorted here? Numbers. The second argument is the number of elements. Well, how many elements are in numbers here? N, 9. That's why I put it into a variable. The third argument is the number of bytes each element takes. How many bytes does an integer take? Size of int. And finally, you want to use the comparator. Which comparator do you want to use? Would it be appropriate to use CMP double ask? Is that a comparator for integers? Nope. Would it be appropriate to use CMP int ask? Sure. How do we pass that over to this other function over here? What is the memory address of that function? The function's name. And again, you can go ahead and muddy it up with an ampersand here. Why? Just go ahead and do this. It's also not correct to do this. What am I doing here? I'm calling the function. That would be like square root and then providing input here. You just provide the name. All right? Now let's see if it works. For int I equals 0, I is less than n, I plus plus. Let's go ahead and print f %d, comma, numbers sub I. And then print f, an n-line character here so that it looks all nice and pretty. I will print it before quicksort and I will print it after quicksort to show you that in fact it is working. So GCC demo. Oops. Demo and film.c. There we go. We'll get to that eventually. All right, running this. So 42 through 0, that's the original right there. And here is the sorted array. Is it in ascending order? Yes. Let's quick sort, but in descending order. Do I need to make any changes other than the comparator that I pass in? Nope. Now it's in descending order. Did I need to re-implement the entire sorting algorithm? No. All I needed to re-implement was this one thing down here, this comparator. Now, I asked before whether or not it would be appropriate to use that double comparator. Let's find out what happens when I do. First of all, it's going to complain. Oh, wow, that's a full-blown error. Wow, good job. I thought I was only going to get a warning about that. The compiler won't even let me do this because, oh wait, no, sorry. It will let me do this as long as I spell it correctly. All right, yeah, okay. I was giving it way too much credit. It probably will not even get a warning out of this. Yeah, it's not able to look that deep into the code and say, wait a second, this is an array of integers and that's an array, that's a comparator for doubles. Nope, that doesn't work. I don't even think if you turn on all warnings would it actually detect something like that. Yeah, it's reporting other things but not that. Let's find out what happens when I try to run it. Predictions, first of all, what's going to happen? So that comparator is going to expect doubles. It's going to expect things that are 8 bytes, not 4 bytes. And it's going to just compare this 8 bytes to that 8 bytes when it only should be comparing this 4 bytes to that 4 bytes. Yeah.
It'll compare 2 integers to 2 integers.
That essentially that's what it's doing, and it'll give you weird garbage results. Is this sorted in ascending order or descending order or any order whatsoever there? Nope. So weird stuff. What if I had an array of doubles that I treated as integers? Even weirder stuff. Because when quicksort goes to change these around, say instead of taking this 4 bytes and this 4 bytes and swapping them because they're out of order, and I told it that, no, you're actually doing doubles instead. It'll take these 8 bytes and these 8 bytes and try to swap them. Completely screwing up your memory, probably, hopefully, eventually you're ending up with a segmentation fault of some sort. Right? Undefined, unexpected behavior. Right? So, take away. Always use the appropriate comparator. And you'll see what happens in your lab tomorrow when you don't. When you don't use the correct comparator on binary search. Speaking of binary search, now that we've got quicksort, what else can we do? Is there a binary search, do you think? Yep, there's a B search. What do you think the B stands for? Binary, right? And so what is its signature? For the, here, find B search. I don't want to type it out. Darn it. Okay, I don't have it. So man B search. There we go. I'm going to cut and paste this. By the way, where are these things? In the standard library. Where's quicksort? Qsort? It's in the standard library. Right? So you've been bringing them in this entire time. So what does the B search function look like? A standard binary search implementation is available, and its signature looks something like this. There we go. So let me go ahead and spread these out here. There, 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 and there. So it takes 5 inputs. A lot of them look familiar. In fact, base, nmem, nel, size, and compare, they are all exactly the same as quicksort. because bsearch needs to know exactly the same amount of information as quicksort does. It needs to know what array you're searching. It needs to know how many things are in that array in order for it to say I start at 0 and my end index is n minus 1. And it needs to know how big things are in order to pass them off to a comparator. And yeah. Why would you need to know how big things are when you can just ask the comparator about them? I'm not sure. I don't know. That's a good question. That's a head scratcher. I'm going to have to look into that. Technically, it probably doesn't need this this parameter right here. But then the last parameter is going to be a comparison here. Okay. Also note here that it's a little bit different, slightly, in its in the array. Up here, it was void star base. Down here, it's const void star base. Why? I'm only searching now. Am I going to be making changes to the array? Nope. I'm just searching the array for the needle in the haystack. So now it has a guarantee that it will not be making changes to the array. Right? So difference is const with the array. It won't be making any changes to the array. Right? And the other difference is there's a new first argument, a const void star key. Right? Remember that we used keys when we were doing linear search and binary search for integers. Here's the key that I want you to search for. I want you to search for 5 in that haystack. Right? Here, it's a little bit different because you're not just searching for integers. You're not just searching for doubles. You're not just searching for films. It is a generic void pointer. It's also const because you're going to be not going to be making any changes to it. Okay? So let's see how that would work over here. So first of all, I'm going to have to not sort it with the wrong comparator here. In fact, I'll go ahead and leave that in there. And then let's resort it by qsort in ascending order. Right? So bsearch demo. Right? First, sort it. Because remember, binary search does not work if it's not already sorted. If it's in random order, as we saw before with our own implementation, and you start going and searching for 42 and it expects it to be on that side, but it's on that side, it misses it. Right? And it reports that it was an unsuccessful search even though 42 was in there. Right? Once I have sorted it, now I can use bsearch. Now, what does bsearch look like? Exact same 4 arguments, but with a new argument in front. How do we go about searching for, say, 42? Search for 42 in numbers. All right. Can I do this? I want to know, is 42 in there? No, why? Well, first of all, is 42 a pointer? 42 might be a memory location. May not belong to you, though. Right? So segfault. In fact, let's find out. GCC. Quiet you. That's not an error. Good. It's just a warning. Right? But that warning is going to result in a segmentation fault. 42 is not a memory location that belongs to you. Okay, fine. I'll go ahead and put it into an integer, x, or key. Did we already use that up here? Nope, not yet. Is equal to 42. And I'll pass in the key instead. Right? Again, segmentation fault. Is key a pointer? Nope. How can we make it into a pointer? First of all, is that the correct way of doing it? Key is a pointer, but then I make it point to the memory location 42. No. I want a key, an integer, that holds the value 42, but now I want to pass that off to this function by reference. So what should I be doing? Should I be dereferencing it? Nope, it's a regular old variable. So how do I make a regular old variable into a pointer variable? Ampersand. Right? Everything's hunky-dory now as far as the compiler is concerned, but it's not reporting anything. Right? So how do I know that it was a successful search or not? Let's go back to the man pages. What's the return type here? Void star B search, right? So what is the return? It returns a generic void pointer. What is the contract of that pointer? The B search function searches an array of objects, the initial number of which is pointed to by base, blah, blah, blah. The contents of the array should be in ascending order, sorted according to the comparison function referenced by compar. Blah, blah, blah. What's its return value? That's what I'm interested in here. It returns a pointer to the matching element member of the array. So in other words, if it finds what it's looking for, it'll return a pointer to that memory location at which it's stored. It's not going to return 42, right? It's going to return a pointer to that memory location that contains 42. Or, if there's no such match, what does it return? The only thing that it can, null. Right? If there are multiple elements that match the key, the element returned is unspecified. There could be multiple 42s. Everything could be 42. It doesn't say that you have to return the first one or the last one or the third one or the fifth one. It's returning an element that matches that key. With our linear search algorithm, we return the first one, but that's just because that's how the linear search algorithm worked. With our binary search algorithm, same thing. It found 42. Okay, I'm done. There's an element. It's not the first, the last, or anything like that. It's an element. So let's go ahead and use that. So int result. And I'll say that result is equal to B search. Does that tell me what index value it's stored at? No. You can get that through pointer arithmetic. I'm not going to do that today, though. Let's just get this done by actually using this. All right. So if result is equal to null, what can I say? Printf no such element %d found. End the line. And I'll go ahead and go with 42. Or key, I guess. That's what I'm searching for, right? Else, printf, element found %d at memory location %p for a pointer containing the value %d and the line. Quit this. Oh no, I think it's starting to screw up here. Come on. All right, so key, the result, and then finally dereferencing the result, right? So let me zoom out here so we can see it all in one. So the key here, that's just the thing that I searched for, right? The memory location here, result, that's a pointer, right? And how do you get the thing stored at that pointer? You dereference that pointer and print it out as an actual value here. I'm going to copy paste this just to make sure that if that does screw up that I didn't lose everything. There we go. Come on. Oh, there we go. cd main, gcc, demo, and what was it? The other one, film. .c. There we go. So should it be a successful search or an unsuccessful search here? Is 42 in there or not? Yes, it is. So it should be a successful search. It was at memory location, blah, 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 containing the value 42. What if I searched for 421? Is that going to be in there? Nope. So the value returned will be null, and it'll print out no such element found. Okay. Let's go ahead and go back to 42. And let's go ahead and use a different comparator. All right? CMP int descending. Is this going to work? Remember up here, I sorted it in ascending order. Binary search has to have the same assumption, right? That it's going to look in the middle and say if 42 is greater, then it's going to go that way. If it's less, it's going to go that way. So if I sort it in descending order, is it necessarily going to find that element? No. because you're using a different comparator. This comparator and this comparator, the comparator with which you used to sort has to be the same as the comparator which you used to search. Let's find out that it is actually going to fail. Right? No such element 42 found. Why? Because I used the wrong comparator here. Right? CMP in double ascending. Now that's super wrong, right? Yep. But at least it didn't segfault. In general, it would segfault though. Right? Okay. Questions on this so far? No? All right. With the remainder of our time here, let's just get started on what it would look like with respect to the films. Right? So let me go ahead and open up film again. So remember that a film is an EIDR, a title, a director, an Internet Movie Database rating. The director itself has a first name and a last name and a date of birth, right? And I just went ahead and made a couple of, get rid of this. I remember that I made 3 films up here just to have some data to play with. Arrival, Blade Runner, and Dune, right? What would a comparator for a film look like? So this comparator orders film structures in ascending order based on ... What criteria could I use to compare a film? A lot of different things. I could do it based on the title. I could do it based on the director, all directors first name, then last name. I could do it based on EIDR. So choose one, first of all. And tell me what it would look like. How do you want to order the films? Title? Okay. Let's do it by title. And then we'll do it based on other criteria next time. Let's just do one example today, though. Ascending order based on title. So is it going to be int CMP film and then film A, film B? Is that a comparator? No. It is only a comparator if it has this signature right here. It takes 2 const void pointers and it returns an integer. There, that's a comparator. Step 1, what do? I force them to become films. So instead of doubles, they'll be film, 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 and film. Now I've got films X and Y. You said that you wanted to do title? Okay. So let's go ahead and outline this. If X's title is less than Y's title, right, I'll return something negative. Else, if X's title is greater than Y's title, I will go ahead and return something positive. Else, return 0. Right. Okay. This is not real code. How do I translate this into real code here? First of all, how do I get X's title, first of all? So we were discussing this at the beginning of the class. Is it a dot operator or is it an arrow operator? Oops, arrow operator. Why is it an arrow operator? Because it is a film pointer. Right? Likewise, Y's title is going to be film pointer. So it's arrow on both of those. Can I use the less than? Now this is a string. This is a char star right here. And this is a char star. Remember that the title is indeed a char star here. Is that how I compare 2 character arrays? I could, but that compares memory addresses. That doesn't say that Blade Runner 2049 and Arrival, the Arrival comes first in lexicographic order, right? So how do I do string comparisons properly? I think I heard it before. What was it? str length would len would give me the length. I have 2 films. I want to know, are they like this, this, or this? CMP, right? And if that is less than 0, then return something -1. Otherwise, if that is greater than 0, then return 1. Otherwise, return 0. That seems overly complicated. If this is negative, return something negative. If this is positive, return something positive. And by exclusion, if these two things, if this returns 0, return 0. Do I have to have all this if, else stuff? Or can I just simply return whatever strcmp returns? There. Again, why use many words when few words do trick? Short, short, short as much as possible. Play code golf, right? Not only that, and I don't say that just to make it simpler, fewer lines of code, fewer characters. I say it to reduce the number of points of potential failure, right? If you have 10 lines of code, then there are 10 lines of code that could be wrong. If you have 1 line of code, there's 1 line of code that could be wrong, right? And if you're using a library function like this, probably not going to be wrong, right? What if you wanted comparing film, or so is this an appropriate name, by the way? If you want to compare it based on title, give it a better name. By title. In ascending order? What if you wanted by title in descending order? Same trick as before, right? Where is it? It's up here now. Call that other comparator with those values swapped, right? What if you want to do based on, I don't know, director? By director name, right? What would it look like then? So what about director Alan Smith and director Benito Smith? Which one should come first? Alan, right? So they have the same last name. If they have the same last name, then you look to the first name so that Alan comes first and then Benito, right? Or whoever, right? It's difficult to make up names, right? So there is going to be a little bit more complicated logic. It's still going to be string comparisons, but then if you've got a tie, you can't just return 0. Smith, Smith, what if the first names are different? So really quickly here, what should it be? Int result is equal to strcmp of x's director. What did I call it? Director, right? And then I want their last name. How do I do that? So be careful here. This is a film star, and so I do use the arrow operator. But once I've done that and I'm looking at the director, is this a person star? Nope. So what do I use? The dot operator, last name, right? And y's director dot last name. Right? Oops, that's not an if. Here, I'll put the if. If the result is 0, what does that tell me? That they have the same last name. Look to the first, dot, dot, dot. Oops. Otherwise, if they don't have the same last name, Del Toro and Villanueva, let's pronounce it correctly, Villanueva? I thought that that's how you pronounce it. I don't think that's how you pronounce it. Villanueva, I think. Denis Villeneuve. Don't quote me. Whatever. Right? Else, if you've already broken ties based on their last name, then there's no need to look at the first name. You simply just return the result. But if they do have the same last name, then you need to look at the first name, which would look like this guy up here, return. But instead of looking at the last name, you would look at first name and first name. All right, we'll pick it up there and test it when we come back on Wednesday.